Hey, welcome to The Explainer. Today we're talking about a secret doctor for fuel cells. Yeah, you heard that right. A piece of tech that can look inside and diagnose problems before they ever turn into a disaster.
Just think about that for a second. What would that be like? No more guessing games, right? No more sudden, catastrophic failures out of nowhere. Instead, you get a clear, super early diagnosis of exactly what's going on deep inside.
Well, for the hydrogen fuel cells that are going to power so much of our future, that technology, it's already here. It's called Electrochemical Impedance Spectroscopy. Okay, it's a bit of a mouthful, I know. We'll just call it EIS. But trust me, it's one of the most powerful tools we have for keeping these critical energy devices healthy. So let's dive in.
All right, so first things first. We have to understand the problem we're trying to solve here. Why does a fuel cell even need a special doctor in the first place?
So here's the real challenge. A fuel cell, for all intents and purposes, is a black box. There are all these different processes happening inside, all at the same time, all overlapping. So when its performance starts to drop, when that voltage goes down, that's just a symptom. It's like having a fever. You know you're sick, but you don't know why. Is it the membrane? Is it the catalyst? Is there a water management issue? And the tricky part is, you can't just crack it open and take a peek inside to find out.
So, how do you peek inside that black box without, completely destroying it? Well, you use something that's basically an electronic stethoscope. And that's where EIS comes in. It is such a brilliant method because it's completely non-destructive. All we do is send a tiny, totally safe little AC signal into the cell, and then we just listen. We measure the response. But here's the real magic. By changing the frequency of that signal, we can actually isolate and look at all those different internal processes one by one.
Okay, so how does this actually work? It's basically a four-step dance. Step 1, you apply that small AC signal. Step 2, you measure how the fuel cell responds. And there's always a tiny delay, what's called a phase shift. Step 3, the machine calculates something called impedance from that difference. You can just think of impedance as a very specific kind of electrical resistance, or friction. And then step 4, and this is the absolute key. We do this over and over again, sweeping across a whole range of frequencies, from really high to really low.
And this is why scanning all those frequencies is so incredibly powerful. See, each frequency acts like a different lens. High frequencies let us see the really fast stuff, like the electrical resistance in the membrane itself. Mid-frequencies, those tell us about the speed of the chemical reactions happening on the catalyst. And the really, really low frequencies, they show us the slow, sluggish processes, like gases trying to push their way through a flooded electrode. It's like having a whole diagnostic toolkit in one.
Okay, so we've got all this data, but a stream of numbers isn't a diagnosis, right? How do we turn all this into something we can actually understand? Well, this is where we learn to read the vital signs.
All that data gets plotted on a special chart called a Nyquist plot. And honestly, the best way to think about this is like an EKG for the fuel cell. The specific shape of the curve, its size, where it is on the chart, all of that creates a unique health signature for the cell at that very moment.
And this is where you can see just how specific the diagnosis gets. Look at this. On the left, you see what happens when the membrane starts to dry out. Its resistance goes way up, and that shoves the entire plot over to the right. But now, look at the right. This is when an electrode is flooded with water. See how the end of the plot, the low-frequency part, stretches out into this huge, long arc? That's the fuel cell basically screaming, "I can't breathe, I can't get my fuel."
And we can put hard numbers on this too. Take a look. Something called ohmic resistance, which is really a measure of the membrane's health, might be around 0.1 in a brand new, happy cell. But in a degraded one, it can easily triple or go even higher. And charge transfer resistance? That tells you how efficient your catalyst is. That can jump by a factor of 10 or more. These aren't just guesses. These are precise, quantitative measurements of what's going wrong.
And this isn't just some weird thing that only exists in a lab. EIS is already out there in the real world, performing these critical checkups every single day.
So where is this doctor at work? Well, pretty much everywhere that matters. In R&D labs, it's helping scientists invent better, more durable materials. On factory floors, it's a quality control tool, making sure every new fuel cell that rolls off the line is perfect. In long-term durability studies, it tracks cell health over thousands and thousands of hours. And what's really exciting is that it's now being built directly into vehicles to give real-time health updates and even predict problems before they strand you on the side of the road.
So what really makes this technique the gold standard? And where is all this technology headed next?
Well, when you really break it down, it's pretty easy to see why EIS is king. First, it can separate out different problems that a simple voltage reading just lumps all together. It's totally non-destructive. We can do our diagnosis without having to tear the cell apart. It gives us actual hard numbers, not just a gut feeling. And maybe most importantly, it's so sensitive it can catch these tiny little changes long before they turn into a catastrophic failure.
And the future for this is even cooler. Right now, researchers are pairing these incredibly rich diagnostic signatures with machine learning and AI. And what that's creating are these truly intelligent systems. Systems that can not only tell you what's wrong right now, but can actually predict a failure weeks or even months before it happens. That's how we're going to keep our clean energy future running smoothly.
Because at the end of the day, building a clean energy future isn't just about inventing cool new tech. It's about making sure that tech actually lasts. And it's techniques like EIS that are absolutely key to making sure our systems are not just powerful, but also dependable. So the next time you're thinking about clean energy, don't just ask yourself, how do we make it? Ask, how do we keep it healthy?